Mota. You can start your talk.
Okay, thank you very much. I will just see how to share my screen. In principle, so I guess you can see it. Can you see my screen? Can you confirm? Because I can. Very good, yes. Because I cannot see any faces, so yeah. So just let me know, yes, if there's a problem. So yeah, so first of all, thank you very much for the invitation. It's indeed a pleasure giving this seminar. So as my title says, I'm going to talk about the viability of screening mechanisms in gravity theories beyond general relativity. And what I'm going to tell you about is that usually theoreticians build up theories of gravity beyond general relativity. So theories of gravity which modify general relativity at certain scales. And they have embed screening mechanisms within this framework of theories of modified gravity, which hide these modifications of general relativity at the scales that we perform experiments. So usually when we have theories of modified gravity, as long as they have a screening mechanism embedded in them, in principle, these theories of modified gravity become viable. Now, what I'm going to tell you about is that there are some nonlinear and high energetic astrophysical phenomena happening in our universe, which may in fact spoil the efficiency of these screening mechanisms. And so not all the theories of modified gravity which have embedded a screening mechanism are real viable. So I will give you all the details so you'll be able to understand what I'm trying to say. Okay, so before going to the theory of modified gravity, let me tell you, at least for the students, what is, oops, sorry. I think you lost, yeah. Can you see it now? Because hopefully you can. Okay, thank you, yeah. So let's start with general relativity. So general relativity is in fact a quite unique theory of gravity. So from Lovelock's theorem, one can see that the only second order local gravitational field equations which we can get from an action in 4 dimensions and which has a metric tensor and some related tensors to it are basically the Einstein field equations with a cosmological constant. Okay, so what it means is that general relativity is a theory that you can get when you assume or where you impose that your theory needs to be local. The equations, the field equations need to be second order, so you don't have higher order equations, which usually lead to problems like ghosts and instabilities. That's when you also impose that you live in 4 dimensions and that the carrier of the gravity interaction is going to be a tensor or some related tensors to it. Okay, so that's what you get. That's general relativity. So when people talk about modified gravity, usually what they mean is that they will have to break one of these conditions for the Lovelock's theorem. So either including higher dimensions, for instance, those are theories that kind of rise, for instance, from string theory, which have 11 dimensions. You have brain-world models with 5 or 6 dimensions. And so every time you go beyond 4 dimensions, you have a theory of modified gravity. You can also claim that there's no locality. So these are the so-called non-local models for gravity. You can also get away with saying that, okay, I will assume that there's no limit for my second order field equations. I can have higher order field equations. And there are some viable theories of higher order field equations which do not have ghosts and instabilities. Some examples are the F of R gravity, Gauss-Bonnet, or Rafa Lifshitz, etc. And the other very general, and in fact, one of the most common approach to modify gravity is the inclusion of new degrees of freedom. So new carriers of the gravity interactions besides the metric tensor. And well, the most common one is going to be the introduction of a scalar degree of freedom. And those are like many different theories of modified gravity, which include scalar degrees of freedom. You can also include a vector degree of freedom, for instance, Einstein ether equation, gravity. You can include another tensor. So instead of just having the metric tensor, you have another tensor. So you have by gravity, for instance, by metric moment, etc. And you can even have theories of modified gravity where you include all these three, only two of those extra degrees of freedom. Like for instance, in Tabriz, there's a theory of modified gravity where you include an extra tensor, an extra vector, and scalar degrees of freedom. So this is basically all the different theories of modified gravity that you can do, and you can basically build them by breaking one of the conditions of Lovelock's theorem. Now, in this talk, I'm going to tell you about extending general relativity by introducing an extra degree of freedom. This extra degree of freedom is going to be a scalar field, and that scalar will also drive the universe acceleration nowadays. So it will be playing the role of dark energy. Okay, so this is basically a modified theory of gravity, which is basically a scalar tensor theory of gravity. Now, one of the consequences when you introduce these extra degrees of freedom to modify general relativity is that you are also introducing an extra force, a fifth force, or the force related to this scalar degree of freedom, because it means particles in the universe, they not only interact gravitationally through the metric, the tensor, but they will also feel this extra force, which results from the gradients of this extra degree of freedom, this scalar field. And that in general basically leads to the so-called the Yukawa correction to the Newtonian potential. So when you perform gravity experiments on your laboratory, you will see, you should in principle be able to see this Yukawa correction, which is this term here that I'm spelling out here, Yukawa correction to the movement and to the dynamics and kinematics of particles in your laboratory. Now, the main thing that at least the young people here in the audience should know is that up to now, there's no evidence whatsoever of gravity beyond general relativity. So for instance, no one was ever able to detect any corrections, any Yukawa corrections to the Newtonian potential, nor deviations from general relativity at different scales. So we perform experiments and we do observations at different scales in our universe. For instance, within our solar system, there are several experiments, and all the experiments agree that general relativity should be the theory that describes the whole gravitational physics within our solar system. Even when we go to astrophysical scales, like when we measure the shift of the orbits of binary pulsars, it agrees with general relativity as well, with extreme precision. So as you can see in this plot, for instance, the theoretical line is the solid line, that's the general relativity prediction, and the dots here are basically, with the arrow bars, are the data from observations from binary pulsars along more than 20, 30 years, and they agree extremely well with general relativity. Well, and as you know, also all the black hole merger observations, the detection of gravitational waves, all that agrees with general relativity. And then also even cosmological bounds, those are not experiments, are more observations, which they also put bounds on the existence of fifth forces in our universe. So if a dark matter particle would cluster more strongly than the Newtonian gravity, we would see deviations on the cosmic microwave background and anisotropies, on the matter power spectrum, etc., etc. Okay, so this is something that's in there. So it means that when you build up a theory of modified gravity, in general, you have to embed in this theory a so-called screening mechanism. Okay, and here I'm going to give you basically a general classification of the screening mechanism in scalar tensor theories of gravity. So these theories of gravity where we have an extra scalar degree of freedom in them. Okay. So, of course, I've simplified a bit my Yukawa correction here. So the corrections to the Newtonian potential have this simplified Yukawa term, which basically comes from the inclusion of this extra degree of freedom. So there's this fifth force, I would say. But in general, you can write a scalar tensor theory in the way I'm writing it here. So you have a non-standard kinetic term That's going to be this Z term here. You have a self-interacting potential. You have a coupling to the energy momentum tensor, which can be in general. So when you write down, in fact, what would be your Yukawa correction to the Newtonian potential, it's going to be more or less looking like this. Okay, it depends a little bit on the theories, but you can write it in general in this form. So this will be the Yukawa correction that in principle, if we live within a framework of a theory of modified gravity, which has a scalar degree of freedom in the gravity sector as well, then that's what you should be able to measure in experiments and observe when you perform observations, laboratories, system, etc., etc. Now, what I've told you on the previous slide is that we don't observe this. So this correction to the Newtonian potential, this Yukawa correction, should be really, really tiny. It should be very, very small. So how do we do that then? How do we do that? Well, there are basically three possibilities here. Yes, since we don't see this Yukawa correction, it means that we either have a coupling to the energy momentum tensor, which is really small. So if this G of phi function, which basically is the coupling between the scalar field and the standard model fields, if it's really small, so let's imagine it's close to zero, it means that this factor here is going to be very small. It's going to be very close to zero. And so the corrections to the Newtonian potential are so small that you won't be able to detect anywhere. The other possibility is to have a self-interacting potential, which is going to be basically inversely proportional to the mass. And the mass is going to be so large that this term here, this mass as a function of the field, is going to be so large that since this is a negative exponential, it's going to be that this Yukawa correction is going to be very small. It's going to be exponentially decaying very quickly. And so again, if the mass is very, very large, basically again, this Yukawa correction becomes very small and you don't see it in your experiments. The other possibility is to give a very large inertia to your field. So that's the case when this non-standard kinetic term, if it is extremely large, so you have a large inertia, again, it's inversely proportional to the Yukawa correction. And so again, this whole correction is going to go to zero. So as you can see, this is basically a way with these three ways of in scalar tensor theories playing with these extra terms that appear in the scalar tensor theory of modified gravity. Basically, you can reduce and you can hide this Yukawa correction from any of your experiments, as long as these terms, the mass, the coupling, or the inertia, are very large or very small, depending on where you perform your experiments. So in general, you can classify your screening mechanisms in these ways. So again, we can, if we play with theories of modified gravity where the mass of the field becomes very large, for instance, so the system, so we make this Yukawa correction to vanish, usually we call them chameleon screening mechanisms. And this screening mechanism can be applied to different theories of modified gravity. For instance, can be applied to the F of R theory of gravity, which is basically a higher order curvature theory of gravity, or to other scalar tensor theories of gravity. So you can apply basically the so-called chameleon mechanism, which I will give you some details in the next slides. The other possibility is that your theory of modified gravity has a coupling to the standard model fields, which will be dependent on the environment as well. So it's going to be very small, again, on the environments where you perform the experiments or you do the observations. This is going to be like, for instance, the Symmetron screening mechanism or the dilaton. So that's now you play with the coupling of the field. Okay. Another possibility is then to play with this non-standard kinetic term. Examples of these screening mechanisms will be going to be, for instance, the camouflage screening mechanism, which basically tells you that when the gradient of the field is larger than a given value, basically you screen away any modifications to general relativity. And so you recover general relativity at the scales that you wish. Another theories which usually also this kind of screening mechanism are theories where you have Mond regime in your theory. Okay, so for values of the accelerations or the force of the gravitational force larger than a given acceleration scale, you recover Newtonian gravity. For scales smaller than a given acceleration scale, you have, for instance, the Mond regime. And there's also the very famous Weinstein screening mechanism, which is also a screening mechanism which plays with inertia of your extra degree of freedom, which basically now, which is basically you can apply that Weinstein screening mechanism to different theories of modified gravity, so to massive gravity, to Lilians, DGP, etc. Okay, so what I'm trying to say in this slide as well is that there are different ways of screening away modifications to general relativity, and you can use these screening mechanisms and apply them in different theories of modified gravity. So a screening mechanism is not the same as a theory of modified gravity. So different theories of modified gravity can, for instance, have the same type of screening mechanisms. Okay? Okay, so I'm going to just give you now some very specific examples for those who are not experts and do not work on this field of how these screening mechanisms work in practice. Okay, so I'm just going to give two very simple examples. So the first one that I'm going to tell you about is the Symmetron screening mechanism. Okay, so the Symmetron screening mechanism is, as I said, is basically a scalar. You have a scalar tensor theory. Okay, so you introduce the extra degree of freedom, so the scalar field, which has a standard kinetic term in this case. It has a self-interacting potential. Okay, and what makes it a scalar tensor theory is that you have a conformal coupling between the scalar field and the standard model fields. This coupling will have this particular choice for the model that I'm telling you about. It's called the Symmetron. So it basically tells that the coupling between the standard model fields and the scalar field is this phi squared term. Okay, and the fact there is this coupling between the scalar field and standard model fields, it means that matter particles, the standard model fields, should feel an effective G, so an effective gravitational constant. So they should feel this Yukawa correction, which is something about this general form. Okay, where you have a coupling term, which now becomes a function of the scalar field, and the Compton wavelength, which basically is the range of the phi force, which also is a function of the field. Okay, so in these theories of for the Symmetron, if you have a self-interacting potential, which is a phi to the 4 function, self-interacting potential, basically the whole dynamics of this scalar field is going to be given by an effective potential, which looks like this. So there's the conformal factor, this phi squared term, which couples to the standard model field. So here is the energy density of the standard model fields, and here's the phi to the 4th self-interacting term. So what it means is that when we are in a region where rho is very large, so in a region where the density is very large in our universe, the effective potential is going to be this parabola term that's going to dominate, not the phi to the 4th term. It's going to be this phi squared term. And the effective potential is basically a very simple parabola. So our scalar field will roll down to its minima, as you know. And when it rolls down to this minima, and we will have this fact because, for instance, this is the case, for instance, in a high density environment like the Earth. The Earth, the density is so high that this phi to square term dominates. So the scalar field on the Earth, or even within the solar system, will go down to its minima. It's 0. The vacuum expectation value of the field is 0. And that means the conformal coupling is basically equal to 1. And if the conformal factor is equal to 1, it means the effective gravitational constant that particles feel is basically the Newtonian one, the general relativity one. And so in a high density region, like we'll say the Earth system, even within our galaxy, this field decouples, this extra degree of freedom decouples from the standard model fields. And if decouples from the standard model fields, it means we do not see, we can perform experiments, on our laboratories on Earth, in our solar system, and we won't be able to see and to detect this extra degree of freedom. On the other hand, if you go to large scales in our universe, for instance, scales like in voids or in the outskirts of galaxy clusters, etc., where the density is much lower, so the effective potential of this field becomes like the Mexican heart kind of shape, and then the field will roll down to either one of the minima, the positive minima or the negative minima. It will roll down to this case. And that means that the field acquires a non-vanishing vacuum expectation value, phi, and that means that the conformal coupling between this field and the standard model fields is not 1 anymore. It's basically proportional to the value of the field on its vacuum expectation value, and that means that in voids or in low density region in our universe, particles, standard model fields, or the dark matter particle baryons will feel this extra force. And in there, this fifth force will be alive, and we should be able to detect modifications to gravity at those scales. So as you can see, this is one very specific example for the Symmetron screening mechanism. Okay, so the idea is that at very high densities, basically, these mechanisms screens away, which means basically hides any extra degree of freedom that we have in our gravity sector, while in low dense regions in our universe, this extra degree of freedom is alive, is kicking, and is changing gravity, and is also driving the universe acceleration at these very large scales. So the other one that I would like to tell you, so we have two examples, is the so-called chameleon screening mechanism. In this case, is the mass of this field, so it means the range of the field, which will depend on the local density. So again, we also have a scalar tensor theory of gravity, which has a conformal coupling to matter, and in this case, this conformal coupling to matter is a linear coupling, and you have a self-interacting potential, which is an inverse power law. So again, in this case, so if you calculate what is the effective mass of this field, which is basically related to the range of the fifth force, is the inverse of the range of this force, we will see that the mass is given by the second derivative with respect to the effective potential, which is given by a combination of the self-interacting potential and the conformal coupling to matter, to the matter density. Okay? So what happens is that if I'm in a low density region of my universe, again, at very large scales, in voids, for instance, my effective potential will be quite wide open because it's going to be built by the self-interacting potential here and the conformal coupling to the matter density. Since rho is very small, this term is going to be quite small, so the effective potential is quite wide open, and that means that the mass is going to be very small. If the mass is going to be very small, it means this term is going to be quite large, and so this scalar degree of freedom is going to be very active, and the force, the extra force, and the Yukawa correction that it produces is going to be very large. On the other hand, again, if you're in a high density region like the Earth, the density is very large, and so this branch of the effective potential becomes very steep, and the scalar field becomes very steep. So it means that the mass is going to be very large, and if the mass is here very large in the Yukawa correction, basically this term becomes very close to zero, and that's why that on Earth we wouldn't be able to detect any deviations from Newton's gravity and general relativity, because on high density regions, basically this scalar degree of freedom will be screened away, will be hidden from any experiment that we do. Okay, so this is the general idea for screening mechanisms within theories of modified gravity. Now, in principle and naively, we would say, okay, so let me just build up my theory of modified gravity, for instance, including extra degrees of freedom. It can be scalar fields or vectors or tensors. And as long as I have one of these screening mechanisms, my theory of gravity becomes viable. And it's a possibility to explain the universe as an alternative to general relativity. Okay, so now my talk really starts, and I'm going to tell you that that's quite not an enough requirement, in fact. So just because you have a screening mechanism embedded in your theory of modified gravity, and everything looks very fine in this sense that you have seen, you know, the screening hides any modifications of your theory of modified gravity in the regions that you perform experiments, for instance, on Earth, on the solar system where the density is very high, neutron stars, black holes where the density again is very high. I'm going to show you that you need to be a bit more careful than that. And for that, I have to tell you first, how do people compute in practice when they do an experiment whether your theory of modified gravity is viable or not. Okay, and for that I'm going to tell you about the post-Newtonian parameter, the gamma parameter, which basically is a parameter, is a parameterization of the post-Newtonian correction, as it says, which basically tells you how much space is curved by unit of rest mass. Okay, so this is a very nice parameter to compute every time you propose a new theory of modified gravity, because it's measured very, very accurately. Okay, so you know that this gamma parameter within general relativity is basically equal to 1. Okay, z is exactly equal to 1. So any deviation, and in fact this happens to any theory of modified gravity, you will create that your gamma, your ppn parameter gamma, is going to be different from 1, and you will see a deviation from general relativity. Now, the Cassini probe, which is a probe is basically as a measurement of this gamma parameter, has a fantastic precision, 10 to the minus 5, on the value, on the deviations of gamma from 1. Okay, so this is the measured value by Cassini, and it's an upper bound that any theory of modified gravity, you know, that for instance will introduce an extra degree of freedom, will for sure change the gamma parameter. Then the deviation, the difference between the gamma and 1 should be smaller than 10 to the minus 5. And as I said, I'm not going to show you that, but in general, if you introduce, for instance, in a scalar tensor theory of modified gravity, you will have that your gamma parameter is going to be a function of your scalar field, your scalar degree of freedom. Okay? For instance, just to be very specific, for the case of the Symmetron screening mechanism, so you have a scalar tensor theory where you have the Symmetron screening mechanism, your gamma parameter is going to be a function of your scalar field, which you're going to have this kind. It's going to be proportional to phi square. There's a free parameter from the Symmetron. This m is a constant. There's the Newtonian potential. So, but what you have to get here is that you have a theory of modified gravity, like a scalar tensor theory. Then your gamma parameter becomes a function of your scalar field in the region that you are measuring and doing experiments to try to measure this gamma parameter. So for instance, if we want to know whether my Symmetron theory of modified gravity is viable in the solar system, because that's where the Cassini probe probes the value of gamma and puts upper bounds on the value of gamma, basically we need then to compute the value of the scalar field in the solar system. You know? So we compute the value of the scalar field in the solar system, you plug it in your expression for your gamma parameter, and you see if this value is smaller or larger than 10 to the minus 5. And so basically you can understand whether your theory that you build up of modified gravity is viable or not. Okay, so let me show you how people in general then calculate what is the value of your scalar field, your scalar, your extra degree of freedom on your theory of modified gravity within your solar system, because it's in the solar system that we measure the Cassini, that Cassini measures the ppn parameter. Okay, so we need basically to compute the profile of the scalar field in our solar system. Well, this is done in a very straightforward way. Basically, you have an action for your theory. You know, this is the general action. It means that you can calculate the Klein-Gordon equation for your extra degree of freedom. So for the case of a standard kinetic term field, like it is the Chameleon and the Symmetron, it looks like in general like this. So this is the Klein-Gordon field equations for your field. If you have a Weinstein kind of screening, so it means that you have a non-standard kinetic term, so these equations, they will change. So it's a bit different, but the idea is always the same. So you basically have to calculate what is the value of your field in our solar system. And for that, you have to solve the Klein-Gordon equation for your scalar field, for your solar system. Okay? And how do people do that then in general? So the way the people do that is that they assume the so-called quasi-static approximation. Okay? And the quasi-static approximation basically reduces the Klein-Gordon equation to this form. So basically, the quasi-static approximation neglects the time derivatives of the scalar field in the Klein-Gordon equations and only keep the spatial derivatives. Okay, and the reason for that is basically it's basically in the sense that, you know, the solar system, or even when you compute the profile of your field in our galaxy, these are computing the profile of our field, of your extra degree of freedom, in virialized systems. So these are quasi-static systems where, although, you know, planets rotate, etc., stars rotates, the whole system is in fact virialized in a quasi-static kind of environment. And therefore, the value of the field within the system does not change in time, in the sense that at cosmological scales, you can have your scalar field changing in time. Like, for instance, if you have a quintessence kind of value for kind of model for your scalar field, as you go to lower redshifts, you know, from high redshift to lower redshift, the value of the scalar field changes in time at cosmological scales. At smaller scales, the value of the field decouples from the background expansion of the universe. Just like matter, you know, the cold dark matter, you form halos, and the baryons, they form baryonic structures like the gas and stars, etc. They decouple from the background evolution of our universe. So you can assume that time derivatives, they live at a completely different scales from the spatial derivatives. So the spatial derivatives, they completely dominate the whole Klein-Gordon equation on the scalar field. Okay, and so what people in general they do, they then neglect the time derivatives because the spatial derivatives are much larger, the spatial gradients. So this is called the quasi-static approximation. And they again, the idea is to compute what is the profile of the field in our solar system, with the aim to plug it in our equations for the gamma parameter and check whether satisfy the Cassini bound or not. Okay, so what's going to happen is that in our solar system, this scalar field will have a given profile, which this profile will change from the fact that the sun is where most of the mass in our solar system basically sits in the sun, and they have the planets around there, which basically they will only slightly perturb our scalar field. So our scalar field will have a given profile, and what will happen is that then particles in our solar system, for instance, the orbits of the planets, they will be affected by the fact that our scalar field has a given gradient. So, for instance, planets in our system will feel an acceleration, which is going to be proportional to the gradient of the Newtonian potential, because there's, of course, there's the Newtonian potential, which has a gradient as well, a spatial gradient in our solar system. But also now the orbits of the planets and particles in our solar system, they will also feel the gradient of our scalar degree of freedom. Okay, so and the idea here is that in principle, if your theory of modified gravity has a scalar field which has a huge gradient, at least as large as Newtonian field gradient, it will be ruled out, because you would see that orbits of the planets will be completely off the one that we calculate from our Newtonian theory or from general relativity. Okay, so the idea from the screening mechanism is that we should basically make it this term here, this extra acceleration, to be very, very small. Okay, and for that, now I need to give it very tiny technical details on how this screening mechanism usually make the profile of the scalar field quite small. Okay, so this is going to be something that's going to be in the thin shell effect, and for that, I'm going to give you the example for the chameleon. Okay, so the chameleon field has an effective potential, which is composed by the self-interacting potential here and the other branch of the potential, which is the coupling to the matter density. So the scalar field will see this effective potential and will sit in its minima here. So this is, for instance, inside the sun or in the outskirts really of the sun. So the field will sit in the minima. However, outside the sun, in the outskirts of our solar system, the density becomes very low, so the effective potential changes its shape, and the scalar field will roll down to a much larger value. So it will sit in a larger value here. Okay? So what is happening, if we're going to compute the profile of the scalar field in a solar system, we should in fact see something like that, that in closer to the sun, in the center of the sun, the field should sit in one minima, and as you go outside of the solar system, the field should recover another volume. And as you can see, there is a very strong profile here for the volume of the field. So there's a huge spatial gradient, and that means that the force, the fifth force induced by this field, is going to be very large. Now, when you have the chameleon screening mechanism or the Symmetron screening mechanism, what is going to happen is that, in fact, the profile of the field is not going to be as extreme as I showed you. But when you do the proper calculation and the computation, you see that the volume of the field, in fact, is going to be pretty much a constant within the sun. And it only starts to change and to have an effective profile when you are on the outskirts already of the solar system. And this profile is going to be much, much smaller. You can't get the example here, but it's going to be much smaller than if you have a scalar tensor theory without the chameleon on the screening or the Symmetron screening mechanism, okay? So the profile of the field will in fact be only at the surface of the sun in a very tiny shell, and that's why it's called the thin shell effect, which is a characteristic, in fact, of the chameleon screening mechanism, okay? So what happens in practice is the following. So again, let's compute how planets and particles, in our solar system, what would be the acceleration that these particles would feel, okay? So the acceleration the particles would feel is the Newtonian one. It's going to be proportional to the spatial gradient of the Newtonian field, which is here represented by blue in my case now. So the gradient of the Newtonian potential is going to be proportional basically to the inverse of the mass of the sun, basically to the distance, okay? So there's a gradient, and that's why particles and planets in our solar system, they feel the Newtonian potential. And it's going to be also proportional to the gradient of my extra degree of freedom that appears from my modified theory of gravity. And due to the screening mechanism, what's going to happen is that the value of the field is going to be very small, and the gradient is going to be very small as well. So if the gradient is so small, it's much smaller than the Newtonian one, that means that this term here, this fifth force, is going to be much, much smaller than the Newtonian force. And then it means that basically planets and particles, standard model fields in our solar system, they will basically not feel any of this force. So the screening mechanism managed to hide away my extra degree of freedom, okay? And that's because the Newtonian force is going to be very small. And when you calculate the ppn per meter, and when you calculate the ppn per meter for this theory of modified gravity, phi is going to be basically sitting on a minima all over the solar system, and that means it's going to be very close to zero. So gamma minus 1 is going to be much, much smaller than 1. Okay? So this was just to give you a very practical and very concrete example how people can calculate and answer the question, is my theory of modified gravity viable or not in the solar system? And usually if you have a screening mechanism like Chameleon or Symmetron or the Weinstein, what you do is that you have a scalar field, a scalar degree of freedom, whose value is very close to 0. So the gamma ppn per meter is much smaller than 1. And also the gradient, so the profile of the scalar field is much smaller than Newtonian profile. And that means this fifth force is much smaller than Newtonian one. So we won't see it. So the screening mechanism is very effective and is able to hide these theories of modified gravity. Now, the title of my talk is that there are some astrophysical phenomena which can affect the effectiveness of this screening mechanism. And they can spoil, in fact, what this screening mechanism is doing to the profile of the scalar field. And what are these phenomena? Well, these phenomena are the following. Okay, so just to be concrete, so as long as my system is stationary, so as long as the solar system remains a very good quasi-static system, then my profile of the scalar field, I should be able to assume it's very much a constant. Like today or in 1 billion years, if the solar system does not change, if our sun is still there, there's no if our sun does not go away, or if our galaxy still has the same kind of quasi-stationary behavior, is visualized, then our scalar field should not change, and I can assume safely that the screening mechanism is very effective to hide away the existence of this scalar degree of freedom. But what if our system is perturbed from external events? And this is what my final part of my talk is going to be about. So let's imagine that I have a binary system of white dwarfs, and where I will have the event of a supernovae. So in a supernovae, what I have a region where the density is extremely high. That's where the supernova is. So for instance, in the case of the Chameleon field, it's going to sit on a minima where the value of the scalar field is going to be fixed to the density of the supernova. Okay? So for instance, here, I'm showing you here, for instance, the Chameleon field will sit in one minima. There's going to be this thin shell effect, so the value of the field is going to be pretty much the same in the whole supernovae. So it's basically, I'm screening away my phi force and the existence of this extra degree of freedom in the supernova. And as I go to the outskirts of the supernova, into outside my galaxy, then of course there's going to be some kind of profile for my scalar field. Now what happens is that if the supernova is there for billions of years, then the profile of the field is going to be fixed like that for billions of years. And that means my screening mechanism is very effective to hide the existence of an extra degree of freedom by the supernova. Okay? Now, when the supernova goes off, what happens is that all this energy, high density of energy of matter in the supernova gets spreads out in fractions of seconds and minutes. And so the density of that region suddenly becomes very low. And that will affect the effective potential for the Chameleon field. So the supernova is going to be fixed in this region, while when it blows away, the effective potential very suddenly changes its shape. And when it changes its shape, what's going to happen is that you will see that the energy that was associated to the matter density of the supernova, which is going to go away, and so will give a kick to my scalar field, and will change the profile of my field when this explosion happens. So the profile of my Chameleon field will get completely changed, and therefore, if I change the profile of my field, it means that I will also change the value of the phi force, the value of my ppn parameter. Okay, so this is something that happens for supernovas going off in the case of the Chameleon field, but there's also a quite different phenomena, which is the production of waves in the Symmetry Model. So the Symmetry Model, as you know, there's this effective potential for high dense regions, which is just this parabola, while in low dense regions, in voids, etc., the Symmetron will acquire a value, a vacuum expectation value, which is non-zero. And that means that you will have produced in the Symmetron domain walls. And the fact is that the universe evolves, structures in the universe form, and the value of this scale of the vacuum expectation value in different regions of the universe will change in time as the structures in our universe are formed and they evolve. So here, what I'm presenting here on the left-hand side, that's basically the matter density in our universe. Okay, so these regions here, red and violets, that's where the density is very high. The black regions here, basically are voids here. And here on the right-hand panel, I'm showing you the vacuum expectation value of the scalar field. So when it's black, you will see that basically the effective potential is just like this parabola. So the field is going to have a vacuum expectation value which is zero. So it means the density is very high. So vacuum expectation value of the universe is very high. And when it becomes yellow or green, it means that the scalar field is going to roll down to one minima or to the other minima. And here I'm going to show you the redshift that this happens. So when I started high redshift, so redshift 1, I see that the whole region is basically black because the density of the universe is very high. So it was zero. But as the universe expands, we come to lower redshifts. the symmetry starts to break, especially in the voids. So that's the region where we have voids, and the vacuum expectation value of the scalar field changes from one value. So this is, for instance, this green. So it means the scalar field has a vacuum expectation value, which is on the negative side of the scalar field, while here the vacuum expectation value is on the positive side. And here is black. These are filaments and galaxy clusters, so very high dense region in the universe, where the vacuum expectation value of the scalar field is basically zero. So you can expect, for instance, that the screening mechanism in these high dense regions of the universe is very effective. So you won't see the fifth force or the existence of this extra degree of freedom in these high density regions. But if you do experiments in voids, for instance, that you can see that the fifth force would be alive. So as you can see from this simulation, the vacuum expectation value of the scalar field fluctuates a little bit. And that means that because regions of the universe, galaxies collide, clusters of galaxies collide. And so these domain walls, sometimes they break. And when they break, they create these waves in my scalar degree of freedom. And these waves, they can propagate and they can change the profile of my scalar field. So as I'm producing these waves in this simulation, and what's going to happen is that if I have the profile of my scalar field, for instance, fixed in a given region of the universe, so when the field sits in this minima, what is going to happen is that the profile of my field will again change in time. Okay? So just like in the Chameleon model, the profile of the field can change because you have these chameleon waves which can be generated from a supernovae going off. The profile of my Symmetron field can change because, for instance, some domain walls can collapse and change the profile of my scalar field. All right, so I'm getting up to the end of my talk. So what is then the consequences, for instance, for an experiment like the Cassini experiment, which basically is going to measure the ppn parameter in our solar system? So again, just to remind you, the ppn parameter for a scalar tensor theory of modified gravity usually is a function of the scalar field. I'm giving you here the expression, just very specific for the Symmetron field. Okay, so the whole idea is that in order to know whether the Symmetron screening mechanism is effective or not, we need to calculate what is the value of the scalar field in the solar system. Okay, so we have to calculate the profile, as I told you, and this is what I'm here showing you. I'm showing you here not the profile of the scalar field, but I'm showing already the value of the gamma parameter, -1, in a log scale in our solar system. So this is the sun is going to sit here in 0, and this is basically the profile of my gamma parameter in the whole galaxy, in fact. Okay, so my solar system is going to be sitting here at about 8 kiloparsecs. Okay, the Cassini bound says that the value of gamma -1, the measured value of gamma -1, has an upper bound of 10 to the -5, which is here in this log scale. So my theory of modified gravity is viable if my gamma parameter, gamma -1, is lower, smaller than this 10 to the -5, lower than this red line. And as you can see, the blue line basically is the value of my gamma parameter in the Milky Way. So as you can see here in this case, in our solar system, the value of the gamma parameter is smaller than 10 to the -5, and that renders this Symmetron model as viable, just like the Chameleon model will have something like this as well. So it's going to be a viable theory of modified gravity. Even, for instance, for your camouflage model, you should also have a gamma parameter which is smaller than this 10 to the -5 value. Okay? Now, again, if the system is virialized, is quasi-stationary, we do not expect that the value of the gamma parameter will change in time, because usually our Milky Way is decoupled from the background evolution in our universe. However, as I just showed you, even if our Milky Way is decoupled from the general evolution, the background evolution in our universe, then can be supernovae going off or domain walls, for the case of the Symmetron model, which collapse, and there will be waves coming from the outskirts our Milky Way, propagating through our galaxy and coming into our solar system. And this is what I'm showing you here in this example. So if there's a wave, for instance, from a supernova going off, that wave will change the profile of my gamma parameter and will transform it like that. So when you have a wave, when we so you say, oh, my modified theory of gravity is viable. But if there is a wave from a supernova coming in, this will change for several orders of magnitude the value of the gamma parameter. So it goes from 10 to the minus 8 to 10 to the minus 2. Okay? And that renders my model not valid because the Cassini probe should be able to detect that change. Okay? So in this case, it means that if there is astrophysical phenomena, very high energetic astrophysical phenomena happening in our universe, and if they produce waves, scalar waves, or our scalar degree of freedom in our modified gravity, those waves can enter into our solar system and disrupt our screening mechanism. And when we do this calculation, so this is what we did some simulations. So it depends, of course, on the amplitude of these, the initial amplitude of these scalar waves, so the size of the supernova, etc. But we can show here that the gamma ppn parameter, with respect to the quasi-static calculated value, can grow several orders of magnitude. That depends, of course, on the frequency of the waves, etc. But what it means is that, in principle, you should see if there are supernovas going off in the outskirts and the nearby in our galaxy, and if we could measure the gamma ppn parameters, we should in fact see oscillations on the value of our gamma parameter. And that would be in fact a smoking gun for the existence of screening mechanisms. So when there are no supernovas, we should see a gamma parameter which is a constant, so below the Cassini bound. But suddenly, if there's a supernova going off, we should see an oscillation on the value of gamma, which would increase. So I finalize with my summary. So in general, for theories of modified gravity, a light extra degree of freedom in the gravity sector is valid if there is a screening mechanism which is efficient enough to suppress that extra degree of freedom at the scales that we perform experiments and we do observations. For instance, in our solar system, in our laboratories on Earth, when we measure gravitational waves coming from supermassive black holes, neutron stars, etc. Yes. However, the naive calculations that people do to calculate the viability and efficiency of the screening mechanism usually relies on the quasi-static approximation. And this can be a bit dangerous because astrophysical events can create waves, and the quasi-static approximation is no longer valid. And if these waves enter into the system where we do where we assume the quasi-static approximation, then, for instance, the viability of the screening mechanism can be diminished, and we can render these modified theories of gravity not viable anymore. Okay, thank you very much for your attention.
Thank you for your excellent speech. Two questions. And do you have my voice?
Yes, I do. Yes, I do. Thank you.
Do you have my voice? Thank you. Can we observe these scalar particles in dark matter experiments? Can we observe these scalar particles in dark matter experiments? Of course, I think there are two ways, one of which is to produce them in the sun. That, of course, seems to have its problems, especially since you have to set up a production mechanism for them, and you also have to do something so that these particles can get inside the protected detectors. The second way that seems to me is that we can assume that in experiments with direct observations of dark matter, the final states of the dark matter colliding with the nuclei can be multi-particle. For example, three particles, the third particles being the scalar particles of dark energy. My second question is, can these dark energy particles be considered a very small electrical charge? You probably know that observations places target on the electrical charge of these particles, but perhaps a very small charge can be considered in the same range. Do you think that using this charged particle explain many of the observations related to the monodic gamma rays or not? I'm glad to hear your thought on these questions.
Right. Yeah, thank you. Yeah, it's a very good questions, in fact. So I'm not expert on the dark matter direct or indirect detection, etc. But what I know from the theories of modified gravity, which is what I work on, there are quite strict bonds on, for instance, of the production of these dark energy particles, these scalar degrees of freedom into from particles from dark matter, from the sun, etc. These are bounds related to action bounds, etc. And people have calculated that. And usually what happens is that if you have a screening mechanism which is efficient enough to hide any gravity, any modifications to the gravity sector, to general relativity, that renders the field so heavy that it's very difficult to produce such a heavy field from dark matter production in the sun or indirect detections, etc., etc. So usually, I would say it's easier to use gravity experiments to try to detect those extra degree of freedoms than using dark matter kind of experiments. Yes, because basically the field is so heavy. But that's a very good question, and there are some bounds. I cannot remember now what is the bounds that we have on the mass of these scalar degrees of freedom. I cannot remember from dark matter probes in there. For the second question about the charge, yes, some people look at whether this scalar degree of freedom could have a charge. The bounds on electrical charge are very, very large, are very strong. Sorry. So it's very difficult to have a model where you have this electrical charge. People, however, they have built up models where you have your scalar field is complex, and then you have some kind of other charges. Not the electrical one, but they can have a different kind of charge from the U1 one. And that also there are bounds from now gravitational wave experiments, etc., which put a bound on this charge of these scalar fields. I do not have in mind like what are the bounds, but those, yes, those are new avenues to try to detect those fields or to rule out these models as well. Yes, so basic looking at effects from the charge and also from the dark matter. Yeah.
In Symmetron models, you assume there is an assumption of Z2 symmetry on this Z2 symmetry has two representations, odd and even, and odd representation. Symmetry can arise from the symmetry breaking of the large gauge symmetry, like U1 symmetry or symmetry. At the first step, if you assume the gauge symmetry as a U1 or SU2, and then if you apply the symmetry, spontaneous symmetry breaking mechanism to this model, you can obtain the Z2 symmetry at the final state. And so maybe this Lagrangians, this Symmetron mechanism, Lagrangians, comes from the gauge theories like SU2, like U1, and in this theories you can assume the milli-charge particles like dark matter particles, and then maybe we can couple these particles with photon, and from coupling we can solve some monochromatic signals.
Okay, yes, very nice. Yes. Okay, so that's very nice. Yes, I never thought about that. I know some people use the Symmetron to be a dark matter candidate, but they follow more a phenomenological kind of approach. And the way you describe it, yes, it would be very nice to have a proper gauge theory which give origin to these Symmetron particles and to connect to the dark matter. Yes, I never thought about that, and I'm not sure that people, if there's any paper where there's the way you describe it is written about that. So that's a very good, very nice idea. And there could be signatures, yes, if they become really charged particles and as a coupling to photons, etc. Yeah, there are of course some bounds. Like there are these axion-like searches for axion-like particles. To a FF dual or to the electromagnetic to F square, for instance. Yeah, the energy momentum tensor. Yeah. That's a very good point.
Thank you. And another comment to the Symmetron. In the Symmetron models, there is an opportunity to have a coupling between this scalar field and Higgs field. And via this coupling, we can this particle maybe can interact with the models.
Interacting with? I didn't hear the last one.
In this models, there is a opportunity to have a coupling between the scalar fields and Higgs particles, and then via this coupling we can explain the interaction between the dark energy particles and standard model particles.
Yes. Yeah. Yes. Well, yes. Absolutely. So that would be more the particle physics, high energy physics approach to this symmetry model. Usually people work on modified gravity, and it's just a coupling to the energy density of the standard model fields, not to the standard model fields itself. So it would be very nice to set up this formalism properly through the Higgs channels, etc. Yes, that's true. Very nice. Thank you.
Thank you. Thank you for your explanation. Another question?
I have a question. May I ask? Okay.
Yes, please.
Thank you very much for your talk. Do this scalar field in any way change not just, for example, radiation, dark energy. So because the equations of motion should be much more complicated here, do we have a more complicated scenario, or it's just as simple as the lambda CDM? Thank you.
Yeah, very good question. Yes, I didn't have time to talk about the cosmology of these models. Yes, so in principle, if you have these scalar tensor theories, like the Symmetron, the Chameleon, camouflage, etc., at the moment you introduce the extra degree of freedom, there should have we have several consequences for the cosmology, both the background evolution and structure formation as well. So structure formation it changes a lot within these theories of modified gravity. Now, the way they are constructed, and in order to become viable, they need to satisfy several constraints. For instance, structure formation, the CMB, for instance, anisotropies, temperature anisotropies, should be very close to the one that we observe today. The Mota power spectrum should be very close to the one we observe today. And that means very close to lambda CDM. And so when you build up this series of modified gravity, and when you impose, the gravity constraints, you have early universe constraints like BBN, the BBN constraints, the Big Bang nucleosynthesis, CMB constraints, the Mota power spectrum, etc. When you impose all of these constraints, you notice that the whole early universe, usually up to redshift 5, more or less 5, 3, 2, it's very similar to lambda CDM. very, very similar. So the background expansion of the universe is very similar to lambda CDM. So, and one reason for that, for you to just to give you the intuition, is that the density of the universe is so high that the effective potential is very steep, is just this parabola. And so the field sits in its minima, the symmetric minima. So the field is as an equation of state which is -1, because the effective minima does not change. The effective minima will only change, for instance, in the case of the symmetron, around redshift 2, 3, 1. So when the dark energy, when basically we want the field to start dominating the universe and gives dark energy, so the acceleration. So, and since the symmetron basically sits in this minima most of the history of the universe, the equation of state is basically the cosmological constant one. Also, all the linear structure formation, it's going to be very similar to lambda CDM. There are, however, very strong changes in the nonlinear structure formation that I do not have time to talk about it, but at the nonlinear scales, for instance, profiles of galaxy clusters, etc., that will have deviations from lambda CDM. But the whole background evolution, the whole linear structure formation is very, very similar to lambda CDM.
Thank you very much. Well, I was surprised with your answer because you see, well, that part about structure formation. I think in this theory and for this fifth force, we don't have any of Newton's shell theorem. So, well, I'm not sure. I should check it, but this fifth force might not be in compliance with Newton's fifth theorem. If that is true, then we must have a structure formation that should happen much more faster than lambda CDM. Have you ever checked this? Thank you.
Yeah. So yeah. So yeah, that I fully agree. So if you have this extra degree of freedom, this fifth force alive in the universe at early times, you will change completely the whole structure formation. Yes, that's the idea. Now, what happens is that when you have these screening mechanisms, you are basically screening away all the modifications of gravity. So you are basically removing, you are deleting this fifth force in the early universe. And this is what I'm trying to tell you here, is that in the early universe, from very high redshift, from Big Bang nuclear synthesis, all the way to redshift, let's say 5, the fifth force is basically screened away, 0. And you can calculate that. People calculated that. I also worked on that, but many people around the world has calculated that. And you can see that basically the fifth force is not present. So all the background evolution of the universe, all the structure formation is basically Newtonian, or it's basically general relativity, because there's no fifth force. The fifth force appears when at low redshift, so usually around redshift 2 or 1, when we want dark energy to dominate. So because these are models to be dark energy, yes? So we want that the scalar field then somehow appears in our universe to accelerate our universe. And in this case, the fifth force appears as well. But at very low redshift, at redshift 1, basically the changes of the fifth force, they will happen at nonlinear scales. So this is one reason. The other one is that the range of the fifth force, this is something I also did not have time to talk about, is quite short. The range of the fifth force is about 1 megaparsec range. And that means that only within clusters of galaxies, you can really see the effect of the fifth force. At scales much larger than 1 megaparsec, you wouldn't detect the effect of this fifth force because the range of the force does not go above 1 megaparsec. And again, the reason for that is just because gravity constraints from the Cassini probe, for instance, make the field to make these theories to be quite constrained. Yeah.
Thank you very much.
Thank you very much. Any question?
It was a pleasure. Thank you.
Thank you, Dr. Mota.